Hello and welcome to session 4. Today we will be having a look at topics which include concurrency, Goroutines, and synchronization in Go. Concurrency is an ability of a program to do multiple things at the same time. This means that a program having two or more tasks will actually run individually of each other at about the same time. Concurrency is very important in a modern software due to the need to execute independent pieces of code as fast as possible without disturbing the overall flow of the program. Concurrency in Golang is the ability for functions to run independent of each other. Goroutine is a function that is capable of running concurrently with the other functions. So when you create a function as a coroutine, it is treated as an independent unit of work that gets scheduled and then executed on any available logical processor. The Golang runtime scheduler has all these features of managing which Goroutine gets executed on which processor and at what time. So the Go runtime manages this for us. Golang has built-in concurrency constructs which are coroutines and channels. Goroutines are lightweight threads. Channels, on the other hand, are pipes connecting goroutines together for communication between them. An important thing to note here is that concurrency should not be confused with parallelism. Concurrency is about handling numerous tasks at once. So this means that you are working to manage numerous tasks done at once in a given period of time. However, you will only be doing a single task at a time. This tends to happen in programs where one task is waiting and the program determines to drive another task in the idle time. Parallelism, on the other hand, is about doing lots of tasks at once. This means that even if we have two tasks, they are continuously working without any breaks in between them. As we just discussed, Golang has built-in concurrency constructs which are goroutines and channels. Goroutine is a function that runs independently of the function that started it. A channel is a pipeline for sending and receiving the data. The channels provide a way for one Goroutine to send data to another one. A Goroutine, as I said, is a lightweight thread managed by the Go runtime. So suppose if we have a function call, I have one on my screen. So here's how we would call that in a usual way, running it synchronously. We have been seeing function calls in the previous sessions as well. So we are quite familiar of how we invoke functions in Go. And yes, we've seen it in the previous sessions as well, where we were invoking functions. Just to highlight one thing, this is a synchronous call here. So in order to invoke the same function as a coroutine, what additionally we need to do is we need to use the go keyword before the function call. So this new Goroutine will execute concurrently with the calling one. So to understand this better, let's switch to some code. Yeah, so if you see at line number 9 here, we create a function which iterates from I equal to 0 to I equal to 2 and prints the value of the iteration the variable I along with the input string that it received as an argument. And after every iteration of the loop, it basically sleeps for 10 milliseconds. Just to highlight one more thing here, because we haven't seen the sleep function before. In Go language, the time package supplies functionality for determining as well as viewing the time related things. The sleep function in Go language is used to stop the Goroutine for at least the stated duration passed to the sleep function as an argument. Moreover, this function is defined under the time package. So if you notice closely, we've imported the time package in our code. At line number 21, we make a synchronous invocation of the function, which we have been seeing at multiple places until now. And if you see the output below, so this the highlighted section is the output for this synchronous call. So as I said, since this call is a synchronous call, so the output, this basically acts as a blocking call, and the output of the blocking call is is, uh, is this one. Since this was called synchronously, it acted as a blocking call from the main function. So the main function waited for this function to execute fully before it went to before the control went to the next lines. At line number 24, we as we just saw on this slide, in terms of the syntax to invoke a function as a goroutine, so we use that and we invoke the same function as a goroutine, but this time yes, just one important thing, we've used the go keyword here in order to invoke this function not synchronously, rather an asynchronous call, or rather as a goroutine. And the argument that we pass here is goroutine1. Using on the similar lines, we invoke another copy of the same function as a goroutine, but this time we pass the argument as goroutine2. So since both the goroutines would iterate from 0 to I equal to 2, and after every print we force our goroutine to sleep for 10 milliseconds, we see an interleaved output here. This happens because when one of the goroutine is goes to sleep after doing a print, the other one may be available to execute, and this basically helps us in avoiding any idle time. So when we run the same piece of code next time, the output may change a little. Yeah, so if you notice closely, the output keeps changing with every run, since the Go runtime would schedule the Go routine available, and which is not in a blocked state. A sleep would basically cause a Go routine to get blocked and wait. So you can consider a Go routine which had a time dot sleep executed from within it would enter a blocked state. So if you see at line number 30, we have another time dot sleep call, and the reason we've added this is because the main function is also a Go routine, and if I don't force it to sleep for 1 second, our other executing Go routines may not get a chance to execute at all. So if I remove the time dot sleep and I try to run the code, so if you see the output, it may change with every run of the code. Yeah, so if you see, the output changes with basically every run of the code, and this is happening because our main thread or the main Go routine, we are not forcing it to wait for the other Go routines to complete. This happens because in Go, the program execution begins by initializing the main package and then invoking the function main. When the main function invocation returns, the program exits. It does not wait for the other non-main Go routines to complete. So in order to make the main function wait for the other Go routines, we intentionally added a sleep here. So adding a time Adding a time dot sleep, I agree, isn't the best solution. There are other constructs available in Go, which we would be having a look at in the coming slides. So to have a look at channels, channels are the pipes that connect concurrent Go routines. You can send values into channels from one Go routine and receive those values into another Go routine. So this is the syntax of creating channels. So we create channels with the main function, and as an argument we use the chan keyword followed by the type of data that you plan to send or receive over the channels. So channels can only transfer data of the same type which they are created with. Different types of data are not allowed to transfer from the same channel. The syntax to send and receive data to and from channels is shown on the screen. So in order to send data to a channel, you use the channel name followed by the arrow operator and then the data that you want to pass. To receive data from a channel, you use a variable where you want to store the read value from the channel into, and on the right hand side you use the arrow operator followed by the channel name. Let's have a look at a code to better understand this. So if you see at line number 20, we create a function which accepts a channel as input. So this channel supports data of type string. At line number 22, we send the hello message on this channel, the hello string on this channel. If I go to the main function, at line number 7, we create a channel of type string, and at line number 10, we call our function as a Go routine, passing the channel just created as an input to this function. So at line number 13 we receive the data from the channel. We try to get the data from the channel, since our called function at line number 10 is writing some message to this channel that we passed as an argument. So we try to receive it at line number 13, and we try to display it at line number 16. So when we run the program, the hello message is successfully passed from the one of the Go routine, which is in our case the send data to channel function is passed from one Go routine to the other, and where we receive the data from the channel and print it. So one important thing to note here is by default the send and the receive calls are blocking in nature. So they block until both the sender and the receiver are ready. So this property actually allowed us to wait at the end of the program at line number 13. So it allowed us to wait for the string to be available on this channel without having to use any other synchronization construct. Like in the previous code, we had used the time dot sleep in order in order to force our main function to wait. So since we are receiving data from this channel at line number 13, this, as I said, acts as a, by default, the send and receive are blocking calls. So our code gets stuck here and waits for data to be available. And since data can be only be available after line number 22 gets executed, so once this Go routine is complete, we will have data available on this channel which main function can execute, and as soon as the data enters the channel, is received on the channel, the main Go routine will get unblocked and execute the remaining code. So as I said, by default channels are unbuffered, meaning that they will only accept sends, and meaning that they will only accept sends if there is a corresponding receive ready to receive the sent value. And we just saw this in the previous example. On the other hand, buffered channels accepts a limited number of values without a corresponding receiver for those values. So in order to create a buffered channel, we just add an extra argument which specifies the buffer size of our channel. So here we are making a channel of strings buffering up to 2 values, and because this channel is a buffer channel, we can send values into the channel without a corresponding concurrent receive available in the code. Let's have a look at a code to understand this better. So at line number 7, we create a buffered channel of type string. Let me change it to buffered one. Yeah. So at line number 7, we create a buffered channel of type string. On line number 10 and 11, we write data on our channel, and since this is a buffered channel now, this writing the data to the channel doesn't act as a blocking call, and the program would continue executing the remaining code. On line number 14 and 15, we simply receive the data and we print it. So if you see the output at line number 10 and 11, we put the message hello and word on our messages channel, and since we are receiving data from that channel and we are printing it, so the output that we see is hello word. So one important thing to note here is that had this channel being a non-buffered channel, the program would not execute, because execution will get blocked at line number 10, since it would since for an unbuffered channel, send and receive is a blocking call, and since the control will get stuck here, since there is no other concurrent Goroutine executing, so there will be no one reading data from the channel that we are writing data to at line number 10. So the control will get stuck here, and the program will basically enter a deadlock. So if you try to execute it by making it an unbuffered channel, yeah, so if you see the output, Golang is the Golang runtime is intelligent enough to detect situations when the code enters into a deadlock scenario. So you better be very careful using channels, because not using them correctly will or may cause your program to enter a deadlock condition.